Welcome to Caltech's celebrated Dr. R. David Middlebrook on real-world design. This tutorial was videotaped at the International Analog Applications Conference in Santa Clara, California on September 30th, 1992. Learn how to make the algebra work for you instead of against you by applying methods of design-oriented analysis to get more quantitative answers with less work. The topics introduced in this tutorial are discussed in detail in Dr. Middlebrook's intensive 3-day course, Structured Analog Design, presented in the USA and internationally both publicly and in-house. Further details may be obtained from Artem Associates, telephone number 909-592-0317 or fax 909-592-0698. Dr. Middlebrook is a professor of electrical engineering at Caltech and a well-known author and lecturer. He is a fellow of the IEEE, a fellow of the IEEE, and one of the world's leading power electronics researchers. Practical, design-oriented circuit analysis and measurement techniques is his primary thrust in educating OEM systems designers and students.
There's always an initial impression when people see an outline of what I'm going to talk about. Well, that's all very elementary and basic stuff. This is what everyone has in college. Not only in college, but at a fairly early level in college. When you see a list of topics, that's absolutely true. This is very basic stuff. So why do I think that it's worth talking some more about it? And so that's the premise of this little talk I want to give, and so that's the first point to set up. And the starting point is this. This green line is a steep ramp representing the rate of information absorption while you're a student. It's pretty steep. And you spend 4 years or thereabouts, and what the Caltech students refer to as drinking from a fire hose. And there's a lot of splatter. But that's the way it is for a lot of very good reasons. So you emerge at the end of your college career, degree in hand, all ready to go out and solve the world's design problems. And then what seems to happen to most people is they fall off a cliff. Because when you start your first job, suddenly the problem doesn't resemble anything that you've practiced, worked on, learned about as a student. And the first thing you discover is the real life design problem is the reverse of all the things that you learned how to do, namely analysis. And so there's a very sharp transient there. And you start a much shallower ramp of learning about how design is really done. And the key to the transition as a consequence of this falling off the cliff is you try to apply the analysis methods that you learned how to do to the actual design problem. And the first thing you discover is that the design problem gives you the answer to the analysis problem. That's the specification. That's all you know when you begin. The design problem is to work backwards to the starting point. How do you put the system together? What values do you use for the various components? This is backwards from most of what you learned how to do. That's the first reason why, as I said in the bottom of the previous picture, this is one reason that many design engineers have a lot of difficulty starting out after making this transition. Because the problem is backwards from what they practiced. The second reason is that suddenly the nature of the problem is at least an order of magnitude more complicated than the things they've had experience with as students. The sort of homework and exam problems that we all do are by necessity simplified, sanitized, constructed so there is one correct answer and all other answers are wrong. Has to be that way for all sorts of practical reasons, but of course quite unrealistic. And the combination of those two sudden differences happening at the same time seems to be what is the cause of this difficulty that many engineers have in translating all the good stuff they know, in difficulty in applying it to actually doing real design problems. And for many of us, it seems as though we never really make that transition. Because what happens when we start out on this much shallower ramp is that we learn how to do design from a completely different approach. Fix up a previous design, twiddle knobs, change things, tweak it here and there until it sort of works. And there's a lot of very important practical things to learn about how to do that, and there's certainly nothing wrong with it. And many people get to be extremely capable and productive designers that way. All of those things I just mentioned are certainly necessary in becoming a good designer. But the trouble is, this transient here is a source of overall inefficiency in the sense that the engineer never really puts to use a large fraction of the stuff he was taught. If even you now look back to your college days and think about how many of those things that you struggled to absorb and learn, how many of them you've actually used, you probably will answer not much. And that's the premise that I'm starting from. That's what I want to try to help you do something about. How to get better value out of a lot of the things that you really know already. Although some of them you may not know that you know them. And that's the center of what I want to talk about, and it goes right back to the starting point of how you approach problem solving in general. Not limited to analog circuits by any means, but all the examples I use, of course, will be in that area. This is the way most of us learn things, starting from way back in high school or even before. This is the conventional approach. Put everything into your model. Simplify things later. That means that you postpone approximations as long as possible. I said exactly these same things to my Caltech class yesterday, the very first lecture of the academic year. This is automatically how students approach setting up to solve any problem, because they're deathly afraid of leaving something out or having to make an approximation. Because buried very deep in their subconscious, because of all the training we all have, is this idea that if you're forced to approximate, somehow you failed to solve it exactly. And the overall connotation is that's a bad thing. That's why you hang on as long as possible to keeping everything around. Finally, you do get forced to make approximations in any real situation. But even then, you still fight it. You say, I better not make an approximation unless I can justify it. So again, that limits the number of approximations you feel willing to make at any point. And finally, a specific student syndrome. The more work you do, the more credit you get. It's almost as though their homeworks and exams are graded by weight rather than content. Again, this is a direct consequence of the standard system. you should be rewarded according to your effort. But, of course, as you know very well in real life, that isn't true at all. You get rewarded by results. Maybe. But you certainly don't get any special credit just for putting in more hours. Well, whether you recognize these things consciously or not, they're at the back of all our minds, because that's the way we all get taught. And the trouble with that is, it's a guaranteed recipe to go into algebraic paralysis. Because as you start your analysis, the equations get longer and longer. They start slopping over onto the second line. And it gets slower and slower, and eventually grinds to a halt. Usually before you get to the answer. And this is the crucial step that most of us go through in a first professional job. This is when you're all fired up and ready to go and solve this design problem, and you write down all the equations you can think of, and you grind this algebra, and you slow down and you get stuck. And then this wave of depression comes over you. What do you do next? And the depression deepens when you realize that even if you could pursue the algebra to the answer, it's a useless answer. What are you going to do with it? Because you've got one equation and 45 unknowns. All the circuit elements. And the only number you know is the left-hand side, which is the answer. That's the specification. So that's a double whammy, you see. You can't get the answer probably, and even if you could, you begin to realize there's nothing useful you can do with it. Because you're not going to get brownie points for getting that huge equation. And its only value is what can be done with it. And if you can't do anything with it, then it was a waste of time getting it. That's because 90% of what we all get taught is analysis. Now, the word design is bandied around a whole lot. And to be sure, accrediting committees for curricula use that word a lot, and they insist that there should be X percentage of design in all these academic programs, properly so. But even those programs that attempt to do that and adjust to them usually include design as an add-on, just right at the end of the course. Well, now you've learned all the principles. Now here's a design example to see what you can do with it. So it's an add-on. And that's better than nothing, but still not too good. Well, that's the premise. That's what I identify as the problem. Not that you don't know this stuff, but you're not practiced in how to apply it to solving real problems. Well, what can be done about it? The goal of learning these things is to recognize that design can and should and ought to be not just tacked on at the end, but integrated throughout the analysis process right from the very start. And of course, it's easy to say that. The problem, as usual, is how do you really go about it in detail? And that's what I want to talk about for most of this time. How you can really adjust the analysis methods to get useful answers from a design point of view. So the solution to that is design-oriented analysis. Those of you who were here last year know that this is my favorite phrase. I hardly ever use the word analysis without that adjective stuck in front of it. For the very good reason, as I just said, that analysis that can't be used backwards for design is a waste of time. No point in getting it. And once again, it's very easy to say those words. The important thing is, how do you really go about it? So let me start out with establishing a context for an overall design problem. So here's a very qualitative structure. Again, I showed this last year. The bottom axis represents the inherent trade-off, accuracy versus simplicity. Notice that it's a double label. They run in opposite directions. A design problem is started somewhere at the left-hand end, which means you've got a very simple model, maybe only a block diagram, and of course it isn't very accurate. But the intention is to progress gradually and evenly from the left towards the right in this picture, gradually making the models more accurate and therefore less simple. And along the way, there are innumerable compromises and trade-offs. That's the name of the game, which I'll emphasize again shortly. The important feature of this picture is that there are going to be numerous iteration loops in the way of your progress from left to right. Because typically what happens as you start out, you make a large number of assumptions. And then you pursue the consequences to see whether you're going to be closer to specifications. And of course, a lot of the times, you find out that doesn't happen, which means you have to go back and adjust some of those assumptions. That's what the iteration loop means. You have to go back and change something that turns out not to be a good assumption. And there are going to be several of those iteration loops. And the next important checkpoint is, where do you terminate this process? You'll never get all the way to the right-hand end, because that's really only an asymptotic limit. Because you're never going to get 100% accuracy without having infinite complexity, even if that were possible. So you're going to terminate this process somewhere short of that ultimate limit. But where you choose to do that is also a very important decision, which should not be just done randomly. And in fact, this is where management exercises a stronger influence on the whole process. Because part of the decision in where to terminate this, of course, is to do with the time available for design and the cost. Not only the cost of design, but the estimated cost of the product as well. So economic factors get introduced very strongly in that decision. You're all aware, of course, engineers want to keep tweaking it until it's perfect, but the manager has to step in and say, well, you've got to stop now. And so that's an important part of that decision. It's also very strongly affected by tolerances. Now, tolerances is a very important feature all the way through design, and the tolerance comes into the picture at the two extremes. There's the tolerance of the components that you have to work with, and that's taken as a given. That's part of your input information. Components are plus or minus 10% or whatever the number is. The other place that tolerance comes in is in the specification, the answer, because the specification also has to be subject to tolerance limits. And so part of this trade-off involved in this decision is the worst case, where worst case combination of component tolerances has to lead to a result which is within the tolerance band of the specification, including worst case not only of the component tolerances, but subject also to the extremes of environment and aging and all the other factors that have to be taken into account. Obviously, if this is an aerospace sort of application, then you'll have to pursue this process much further towards the right. than you would if it were a low-cost consumer application where the cost part of it is a much larger piece of the decision. But all of those things are what determine the termination point. So those are the important features of this little picture, and I always like to keep this in mind as a context of all of the detail that we talk about in how to go through these various steps. This is what your overall objective is. There's a couple more things to say about it, even in this general picture, and that is, where do computers fit into this? Well, they fit in best towards the end. Computers are very good at doing the worst case calculations. But that's really when the design is essentially finished. Now, computers can also be useful in the design process itself, which is further to the left in this picture. But I think we have to be aware of some potential hazards here. Hazards which in fact are growing more severe rather than less. A lot of companies, especially big ones, with the best motivations, are tending to plunk a workstation in front of every design engineer. That's very nice. But there's an immediate tendency for that engineer to throw the entire problem into that workstation very early on in this process. And unfortunately, that can often lead to more delay rather than less. Because much of the software in those computers is highly complex, and to use it effectively, you have to know a whole lot about the computer algorithm. You have to know exactly how it's doing the calculation in order to know whether to believe the answer or not. Everyone's familiar with the adage, garbage in, garbage out. But you also have to remember that you can put perfectly good stuff in and still get garbage out. Not because the computer made a mistake in the usual sense, but its algorithm is subject to multiplication of round-off error. And that's a very important topic, which often tends to be neglected. Anyway, the bottom line of that is, if you try to put too much into the computer at the beginning and just wait to see what it tells you, the trouble is it tells you far too much, in one sense, because you get reams of output, but it doesn't tell you anything about how it got that way. That's the real difficulty. Because if you don't like what it tells you, and 95% of the time you don't, because you're still early on in the design, then it gives you very little insight, or practically none, in what to do to change it, and in which direction to change things. So I think you have to be on your guard against expecting the computer to do very much of your design thinking for you. That's dangerous. Now, this is certainly an arguable point, but I stand by that opinion, even though I may be fighting a rearguard action. That's one generality to say about this. The other is, I mentioned that the objective is to progress from left to right smoothly and gradually. For the same reasons, really, that I mentioned you should be sparing with the computer. If you try to start too far downstream, that means you try to make a more complicated model to begin with. Again, you can end up losing time rather than saving it. For the same reason that if you try to take too big a jump anywhere down the road, you can end up losing time. Because if you change too many things all at once, it takes you longer to sort them out in the result as to which changes caused which effect, and therefore it takes you longer to find out which things to change. So the desirable design objective is a smooth, gradual progression from left to termination point in this picture. And as I said, as a design engineer, you're living inside this box, but there's people outside looking on. The project management and possibly the design review committee. And I'll say a bit more about design review committees as we go on. Now, I drew several iteration loops in that picture, and here's one of them. We're now zooming in on one of the loops and seeing in a little more detail what's inside it. And here's the typical sequence of events as you go through one of those loops. Notice this applies to any of the loops. That is, at any particular level of model, whether it's a very simple one or whether it gets more complicated. What you do in going through the loop is follow these steps. You analyze the model. You get a result, and you simulate it, maybe on your computer, and eventually you may measure it. Depending on what the nature of the project is, you may do both of those in succession. If you're designing an IC chip, then you don't do much of the direct measurement because you've got to do a lot more of it with the simulation first, because you can't go and breadboard it in discrete fashion. But in general, this is what the sequence of events is. Now, as you go through that sequence, there are all sorts of internal little feedback loops, because you keep having to go back and check almost with all possible combinations essentially are involved in these little feedback loops. Because whenever you achieve some partial answer, you have to keep checking it to see whether you believe it or whether it meets the specifications or ultimately would do, and you keep having to go back and change things. Notice some of these feedback loops go back to the analysis itself, which is, for the first time here, an indication of the fact that analysis is not some fixed edifice. It's not some fundamental truth which is unchangeable, immovable, that you simply have to work your way through. Instead, it is something which is malleable, something that you can control. And that's really the essence of the main points that I want to talk about. That means that when you follow these particular little internal feedback loops, there is something you can do to change the analysis. And by that, I don't mean correcting mistakes. I mean, even if it's correct in the first place, in that sense, you can express it in different formats to expose different useful things. And that's one of the most important techniques that I want to get into. So all the way around these internal little loops as part of the iteration process, again, overall, you have the project management and the design review committee watching what's going on and getting reports, both written and oral presentations. That means that all the way along this, and now I'll take those away because it gets too cluttered if I put everything in there. That means that all along the way, you have to be producing documentation. And this is an important factor for connection with the design review committee and the project management. And the ideal sequence, again, would be the complete cycle of one of these iteration loops would be the following. What are the possible outcomes if you're proceeding to the end of this particular cycle? Well, the best outcome, of course, is that when you do your simulation and measurement, that they agree. And so now that confirms that your model and the analysis and simulation are correct. So no change needed. The other possibility, of course more likely, is that there is a discrepancy. And then either the designer himself or possibly with the help of the design review committee will have to decide whether the discrepancy is explainable in some simple way and could be ignored, or whether it requires another iteration. That's part of the control function. Now that's a complete cycle with all the steps present, but all too often some of those steps are missing. And most usually the step that's missing is the analysis step, for the reasons I mentioned already. You tried to do that once in your first job, gave up, and never went back. So typically you start with the model and you immediately go to the simulation. Well, the best outcome, of course, is it worked, in which case you're home free. But the trouble this time is, if it doesn't work, if there is a discrepancy, you have to iterate the cycle, but it's harder and longer in the absence of the analysis, because you don't know why the simulation gave the answers it did. So this is the disadvantage of not pursuing the analysis step. It's a cut and try process. Also, perhaps even more frequent, all of those steps get missed out. And you simply breadboard the model, the actual system, and see what it does. And what do you learn from that? Well, it probably isn't going to work properly, at least not totally. And so comes report time to the design review committee, and all the design engineer is able to say, well, it's sort of working. And all the design review committee is able to say is, well, looks as though it's coming along okay, carry on. And so the design review process is sort of a waste of time, because the design review committee simply has to take the word of the design engineer that what he did was okay, because he isn't going to show it, at least not in an interpretable form, even if there was any of this stuff in the previous steps. And that means they can't offer any feedback, and that's the value of the committee. Okay, going back to the total picture. Let's look inside now with further zooming in on what's inside these individual boxes. How do you set up the model? And again, all of this picture is repeated with each iteration loop as the model becomes more complex and, you hope, more accurate. The important thing at every step, at every iteration point in that overall process, the model should contain only the things that are necessary to give you the specific answers that you're looking for at that time. And specifically, answers to the degree of approximation represented by the degree of approximation in the model. There's no point in having a great disparity between the accuracy of the model and the accuracy of the analysis or any of the other steps. They all have to be at comparable levels of accuracy. Otherwise, again, it's an inefficient process. And the important thing about the model is it should have just enough information. And it's just as important not to have too much as it is important not to have too little. And usually only one half of that statement is consciously recognized. Because, as I said at the beginning, the conventional approach is put everything in the model and leave things out later if you're really forced to. But that's one of the difficulties that leads to this roadblock, where you can't complete the analysis. In other words, as in so many things, it's the happy medium which is the desirable objective. Just enough, but not too much. Okay, now I've already mentioned in anticipation of most of what I'm going to talk about is that you can control the analysis. That's the methods of design-oriented analysis that I want to talk about. Simulation, of course, is done using all the computers and software that's available, very powerful. Measurement techniques, instrumentation, and so on. And the documentation of all this, again, is something that the design engineer has great control over and needs to give considerable attention to, which is a direct beneficial consequence of using these methods of design-oriented analysis, because not only can the designer himself see what the answer is telling him, but other people, like the design review committee members, can also see what that result is saying. And that's equally important to get the value out of the design review committee. Well, here's some boxes put around those various things, simply to identify who's responsible for achieving those results. The green part of it is techniques, methods of analysis or whatever, which are originally provided usually by the academics. They're the people who do some of the basic research, certainly as far as methods are concerned. In industry, it's the managers, the supervisors who provide the facility, provide the labs, the instrumentation, the computers, and the workstations, and so on. And there's one box in the middle that needs the contributions of both. And again, that's an important part, often, unfortunately, rather sadly neglected. But both the academics and industry managers can do a lot more to help in that direction. In fact, I wrote some things to emphasize that. He wrote it in red just to say how important it all is. Industry management can exert great positive influence toward better and more cost-effective designs through the documentation process by insisting that the documentation be presented in these design-oriented forms. Those methods of design-oriented analysis that I'm going to describe in more detail not only help the design engineer, but they also help the project management, because the documentation and the presentation of those results is that information transfer point. And that can be greatly improved. So that's a sort of intermediate point that when I am talking to an audience of people already in industry, and some of you are managers, no doubt, I want to put the challenge out to you as managers. You can do a lot more to get your design team to be more productive by insisting on presentation of results in these ways. Okay, let's get back to the detail now. What is design? A very fuzzy word, bandied about a whole lot by a lot of different people, and it's very difficult to pin down exactly what it's saying. Mathematicians have told us from day one, if you're going to solve a problem mathematically, then the number of equations you need to set up must be equal to the number of unknowns you wish to solve for. That idea is embedded in us from the beginning. The trouble with this is, the people who get to us first are the mathematicians and the scientists. We don't hear from an engineer until we're well into college. And by that time, our thought processes have been established by the scientists and the mathematicians. And the problem with that is that engineers face practical design problems in which the number of equations is less than the number of unknowns. Not only less, but much less. by a huge factor. And whether we realize it consciously or not, and most of us it's only unconscious, whenever we face a real design problem and we recognize this, we have a negative feeling about it. This is an impossible problem, because the mathematicians told us it was impossible. But of course, being engineers, we have to solve it anyway. And presumably that's why we choose to be engineers, because we enjoy that challenge of producing something that works, that accomplishes something. We're not trying to push forward the frontiers of scientific knowledge. We're trying to apply the known principles and do something useful with it. And that's a different sort of problem from scientific research. And this is the different starting point. And it's always going to be like that. What we need to do basically is replace that implicit negative approach with a positive approach and find out all the things we can do to solve the problem anyway. So, ultimately, design is solving a problem, in some sense optimally, that's fuzzy of course, by finding substitutes for the missing equations. And it's not going to be perfect, because they are missing. And what you have instead is the best you can do in place, which involves inequalities, approximations, assumptions, and trade-offs. And the basic point about replacing this inherent negative attitude that we all grow up with, replacing it with a positive attitude, is recognizing that doing these things is good and not bad. That's all it takes. It's simply an attitude. And you see how that is the reverse of the conventional approach, where you put everything in, you postpone approximations, and you better be able to justify them when you finally have to make them. The positive approach is completely the opposite of those things. By recognizing that doing these things is good, that's the way you're going to get engineering design answers. And therefore, you should look to doing as many of these things as possible. The opposite of trying to avoid them and postpone them. Get all the benefit you can from these as early as possible in the whole process. We need all the help we can get. Okay, now this is one of the two main ingredients of the positive approach to design. Recognizing that these are good things and you should practice doing them as often as possible and learning how to manipulate them. And it's to some extent, in fact to a large extent of course, an art, not a science. One of the most popular textbooks in electronics is called The Art of Electronics. That's a book that attempts to build on this sort of approach. And we are, in effect, a kind of artist when we make a design. Not only in electronics, of course, but in any engineering field. That's really the difference between engineering and science. So this is one of the important ingredients. The other one is we do have a few equations. And what we need to do is extract the maximum value out of those few that we do have by making each equation work harder. Now again, the mathematicians have told us, don't bother looking. One equation, one piece of information. But that isn't really true from an engineering point of view. There is a lot more information that you can extract other than the single number that you get for the left-hand side after you substitute numbers for all of the things on the right-hand side. That's the mathematical single piece of information that you get. One answer for one set of numbers. But there's a lot more information you can get out of that. And this is where I introduce another term. The way you get more information out of that one equation is by expressing the result in a low entropy form. And I introduced this term in the seminar last year, and I'll repeat this part of it because this is an important starting point. What is the entropy of an expression? It's a word that I borrowed from physics, just because it is familiar in that context. It has a quantitative definition in physics, but we don't care what it is because I'm borrowing it only in a qualitative sense. And the only thing to know about entropy is it's a measure of disorder. The more disordered a system is, the higher its entropy. I'm applying this now to an equation, an expression, the result of your analysis. The gain equals a mess of symbols. It's a high entropy expression if the right-hand side of that equation is just that, a mess of symbols. The way it comes out of the algebra. And that's the way most of us do it. It's certainly the way we all do it the first few times. Because we think we've done well to get any answer at all. And so, however it happens to come out, however the symbols are grouped and arranged, there isn't any arrangement or grouping. It's just however they happen to come out of the algebra. And of course, it doesn't convey any additional information other than what you get just by plugging in the numbers. What we need to do is go to the opposite extreme. A low entropy expression is one in which the terms and elements are ordered and grouped so that their physical origin and relative importance transmit to you some additional information. So you can see which ones are important in determining the result and which are not. That's the first level of additional usefulness you can get out of the equation. Remember, the objective is, from a design point of view, you have to work that equation backwards in order to find out which elements to modify in which direction in order to make the answer come out closer to the required specification. So how each of those elements shows up in the result determines its degree of importance. So that's what I mean by a low entropy expression. Because that's the only analysis result which is potentially useful for design. It's the thing that makes possible working the analysis problem backwards, and if you can't do that, then it was a waste of time getting that equation. So, design-oriented analysis is analysis that keeps the entropy low at every step along the way. That's the next step of improvement in the analysis method. I introduced the word entropy in reference to the answer. And one way to get that is to do your usual analysis, which is sort of turning the crank and getting the answer in whatever form it turns up. Then looking at it and seeing how can you arrange those terms to give you more additional information in terms of insight. That's one way to do it, but it's not the most efficient way. This is the most efficient way. Keep the entropy low all the way through instead of letting it rise and then having to lower it. The analogy of the name carries over to that process also. In a physical system, to lower the entropy, you have to add energy to it. To lower the entropy of an expression, you have to put mental energy into it. And doing it all at the end is not efficient. This is a more efficient manner, which is to control, adjust, direct the algebra as you go along to keep the entropy low at every step. Again, those are techniques that as students we barely hear about. Instructors, having some experience, often do this themselves. And they'll do something on a blackboard and write some equations and do some analysis, possibly in quite low entropy form. They won't use that word. And the class looks at that and thinks it's magic. Because when they start to do the homework problem, they get stuck with the algebra again. And they say, well, the professor seemed to be able to do it in no time. But you never find out how to do that until you get out in the real world, and then with a much longer time scale, by hard experience, then you begin to learn how to do some of those things yourself. But it's not efficient at all. And it takes a long time, and many of those things you never do find out how to do. All engineers like block diagrams, so I made one to represent the design process. This is the usual approach. You start with your model. Again, this applies to any of those iteration loops, whatever the level of accuracy versus simplicity exists at this point. You do your corresponding analysis. You get the result. You compare that with the specification to see if you're close. If you are, fine, but if not, what are you going to do? Well, you go back to the beginning and you make some fairly arbitrary changes, because the high entropy analysis you normally go through to get this doesn't give you any help, or very little help, in going back to see what to change. So what you need to do is close a design feedback loop around this. So you compare the result with the specification, and if there's a discrepancy, that corresponds to the error signal of the servo mechanism. It's the error between the output and the reference. And what you need to do is to use that error in a feedback mode to make an adjustment of the starting point, which is the model or the values, automatically in the proper direction to correct the answer and make it match the specification more closely. That's how a servo mechanism works. And the key to closing the loop, of course, is being able to work the analysis backwards. That's provides that entire block. It makes this forward path, if you like, bidirectional. And that's what closes the feedback loop. You can press the analogy even a little further. You get the usual benefits of a feedback loop. Faster response. You can control the overshoot. Of course, you also have to face the hazards, possible oscillation. But again, there's methods of doing that too. The point is, the design process is made more efficient. In particular, it's made shorter, because you have an automatic adjustment of the design in the proper direction. And of course, the final output of those things is always going on to the next step, which is simulation, and providing documentation for review by the management committees. That's the end of the motivational part of this talk. I feel as though I'm sort of a missionary to try to persuade you of the possibility and then the benefits and the value of some different perspectives on design. And the rest of it is now going to be taken up. We're going through quite a few very specific things that enable you to get low entropy expressions and do design-oriented analysis and control what you're doing. I'm going to talk about some of the specific methods now. This is the proof of the pudding, of course. It's easy to do all this hand waving and say all these fine words. The real point is, how do you really do it? So here's one of these iteration loops. And looking inside the analysis box, which is where most of these techniques apply, although some of them apply later on, this is some of the techniques that I'm going to summarize now. How to express the answer in low entropy form. Doing the algebra on the circuit diagram is one technique. Using normal and inverted poles and zeros, using numerical values to make analytic approximations, and improved formulas for quadratic roots. And I'm going to summarize each of those now, showing how the problem arises and specifically what you do about it. There's a very simple circuit example, a linearized model of a single-stage common emitter transistor amplifier. The transistor, as usual, is represented by a small signal linearized AC model consisting of a collector current generator, beta times the base current. The RE represents the nonlinear emitter diode exponential slope resistance. That's the nonlinear element. The linearization consists of assuming that the value of RE stays fixed regardless of the AC signal that may be going through it. The value is chosen to represent the particular DC operating point. But by assuming that it's fixed for the AC model, that's how you linearize the model. Well, that's not the important thing for this example. It's just any linear circuit model that we start with. If you suppose the objective is to solve for V2 over V1, the voltage gain, I've called it A sub M. M stands for mid-band, representing the fact that the model neglects all of the reactive effects. So the mid-band gain, by doing brute force analysis, which in this case would be loop or node analysis, it turns out there are two loops in the model. Looks as though there are three, but the third one is redundant because the properties of this current generator show that the third loop current is a fixed multiple beta of the second loop current. So it's really only a two-loop circuit. And if you solve those two Kirchhoff law loop equations simultaneously, which is the standard approach, this is the answer you get after 3 or 4 lines of algebra. This is the blind, brute force, turning the crank kind of algebra. The result comes out always in this form: ratio of sums of products of the various circuit elements. In this case, since it was a two-loop model, you get sums of products 2 at a time. If it were a 5-loop model, you would get sums of products 5 at a time. You see how the algebra escalates rapidly with the degree of complexity of the circuit. So that's fine when you do simplified little homework examples, but when you get to the real life problem, it's an order of magnitude more complex, and that answer, even if you can get it, is hopelessly complicated. That's the essence of the problem, the reason that the analysis simply gets out of hand. Okay, that's the high entropy form. Can we put mental energy into this to create a low entropy form? And I went through these steps in last year's talk, so I won't go through them again. But this is the bottom line. It's a matter of seeing how you can arrange and group these terms so the result exposes some useful things. And in particular, in this case, what this result exposes, and I emphasize this is identically the same equation. There is no approximation or anything. It's identically the same, but the two forms hardly resemble each other at all. But the reason they don't resemble each other is that the second version gives you several additional pieces of information. Namely, the RB over RS plus RB is immediately identified as a resistive divider in front of the whole model. numerically, it has to have a value less than 1. Which means that if you want to achieve a certain value of gain, the other factor has to be bigger than 1 by enough to overcome the loss of the first one. That's useful design information when you come to choose values. So that's one piece of information. The second one is all of the resistances in the model, which would generalize to impedances, show up in one of two forms, either as ratios, in this case a voltage divider ratio, or as series parallel combinations. And the value of that is, you know that a series combination is dominated by whichever value is larger. You know parallel combinations are dominated by whichever one is smaller. So when you need to change values, you know which ones to change and in which direction. That's extra useful information. The third piece of useful information is the beta shows up explicitly only in one place. It's inside the alpha as well, but alpha is beta over 1 plus beta, and you know that beta is a large number, and alpha stays almost 1. Now, beta is a particularly important parameter in this result because it's the one subject to the widest tolerances. It's a poorly controlled device parameter. The device manufacturer tries to make it as big as possible. But it is a very variable parameter. So one of the important things to know about an amplifier design is what is the sensitivity of the amplifier gain to the variations of beta within its tolerance range. By expressing the result in this low entropy format, you can see that the beta shows up in the second of two added terms. In other words, the variations of beta are subject to a dilution factor. For example, if beta vary plus or minus 20%, and if those two terms labeled 1 and 2 happen to be numerically equal, then the resulting variation of the gain would be the beta tolerance divided by 2. That's the dilution factor, resulting from those two terms being equal. So you would get only a plus or minus 10% variation in the resulting gain. And if the two terms are not equal, of course the dilution factor is different. But you know what it is. And again, if you need to change that to meet specifications, you know exactly which values will do that for you. So those are the extra benefits. That's 3 more pieces of information in addition to the plain number that you get from one equation. Any grouping contains more useful information than the simple high entropy form that comes out automatically from doing the algebra. At various points along this, I put some little bottom line comments from the point of view of project managers who are looking at reports and presentations from your design team. And so here's what I suggest as an objective. Don't accept analysis results that show element symbols as sums of products. That's high entropy. It's undigested. It's very little help. Insist that your design team put the results into low entropy form, even if they didn't derive them in that format to begin with. This is how you can exert influence over your design team to improve their productivity. Now, that was putting the mental effort in to lower the entropy of the answer after you've already got a high entropy one. As I said, that's not the most efficient way to go about it. More efficient way is to keep the entropy low all the time, which means that you don't even attempt to do loop or node analysis. By its nature, loop and node analysis means solving the entire system in one lump, because you write n simultaneous equations by invoking Kirchhoff's law. Once you've written those n equations, you've finished with the electronics. The rest of it is simply algebraic manipulation, which consists in solving and simultaneous equations in which the result is a ratio of two determinants. And that's how most of the computer software programs solve it also. And it involves inverting a huge matrix, which gets into all sorts of numerical difficulties, which people are well aware of, and there's all sorts of methods set up to deal with that. But it's simply pushing the problem off to a different order of magnitude. The whole point about doing analysis in a low entropy manner can be summarized by saying divide and conquer. Don't attempt to solve it all in one huge lump. Break it down into as small, separate little pieces as you possibly can. And there's all sorts of tricks to do that. And here's one of them. The very first theorem that you learn to do with electric circuits, Thevenin's and Norton's theorems. And if I ask students, and I usually do this every year, because they've all had a first course where they did these theorems, I ask them, what do you know about Thevenin and Norton? And so they wheel out the usual statement of how you apply the theorem. You replace the network between these two terminals by an equivalent voltage source and impedance, and they can give you the rule for finding those, because they've done lots of examples in how to do that. But then if I ask them, why is it worth doing that? No one knows. And if I were to ask you, who've been out there a long time, how often do you use those theorems in your work? I would suspect that the answer would be not much. For that very reason. You were very adept in applying it, but no one bothered to tell you why it was worth doing. The real value of Thevenin's and Norton's theorems is every time you use one of those theorems, you reduce the number of loops and nodes by one. Because this network, for example, if you replace this by a Thevenin equivalent, you've reduced a two-loop circuit to a single-loop circuit. If you replace it by a Norton equivalent, you've reduced a two-node circuit to a single-node circuit. Which means in the complicated case with multiple loops and nodes, if you successively apply those theorems, you can reduce the number of loops and nodes one by one and reduce the result to maybe even a single loop, and you write the answer in one equation. Because every time you do that reduction, you are effectively solving one of those set of simultaneous equations. So you solve the equations sequentially instead of all together. There's a free bonus in the answer. Every time you make the circuit simpler, the element values, of course, get more complicated. But they get complicated in a low entropy manner because the series parallel combinations appear automatically by application of the theorem. And you don't have to look for them. You don't have to think them up, which is what you do when you try to lower the entropy all at once at the end. If you do the analysis this way, the low entropy forms automatically show up, you see, as ratios and series parallel combinations. You don't have to think. So that's the free bonus you get by doing the solution sequentially instead of all at once. Okay, so this is the value of using those theorems. You reduce the number of loops and nodes. And more generally, you replace the simultaneous solution of multiple equations by sequential, simple steps, doing the algebra on the circuit diagram. The next technique of design-oriented analysis I want to talk about is normal and inverted poles and zeros. Normal poles and zeros you know about already, except you don't call them normal. That's because you don't know of any abnormal ones. But since I want to introduce a different kind, then I have to have a special adjective for the ones you know about already. So they are the normal poles and zeros. Well, how does this point arise? Here's a simple little frequency-dependent transfer function of a simple network. The usual approach to analysis of this would be to write it from an impedance divider, or actually by doing some of the algebra on the diagram. A shorter way to do it would be to absorb the two resistors into a Thevenin equivalent and reduce the circuit down to a single loop. That would be the easy way to get the answer. But anyway, most people would arrive at an answer in the standard high entropy format, which is a ratio of sums of products of the various circuit elements. And most people would consider this format to be the answer. Then they plug in numbers. And this is the numerical answer. Again, here's a bottom line comment addressed to managers. If you see this sort of result in a report, send it back. This is not a useful format for the result. You could put it into low entropy form, because the next step, whenever you get a ratio of polynomials in complex frequency S, the next step should be make those polynomials have a leading term of 1. That is, you should pull out the R1 plus R2 from the denominator out front, and the R2 from the numerator out front. And that gives you this format, where the A0 is the R2 from the numerator and the R1 plus R2 from the denominator. And then you have to divide the R1 plus R2 into the S coefficient, and the result is a C1 with an R1 parallel R2. And you would get that result directly if you did the analysis by Thevenin reduction. That is, you wouldn't have to search for those low entropy forms. They would come out automatically by themselves, which is a benefit, of course. In any case, the result ought to be expressed in this format, because now these two parameters, A0 and omega y, are the parameters that describe the shape of the frequency response, and that's the answer you're interested in. If you plot that in the usual asymptote format of dB versus log frequency, which of course is really a double log scale, you get the usual result of this function, which is a single pole function. Roots of S in the denominator are the poles of the system. So this is a linear function of S. There is a single real pole at S equals minus omega y. It's a left half-plane pole. That's the normal pole, the one you're normally used to having. The important point about this so far is this is a low entropy format, because when you make this sketch, these two quantities are immediately visible, and you know immediately what the interpretation is. The A0 is the zero frequency gain, which is flat. The omega y is the corner frequency, namely the intersection of the zero and infinite frequency magnitude asymptotes. Of course, the actual magnitude function has a smooth 3 dB down corner at that point. But the geometry of that corner is fixed. It's always the same. Whenever you have an asymptote intersection like that, there is always that same geometry smooth curve that goes through that point. So you don't have to draw it all the time. You certainly don't have to plot it. This is a sketch. You can do it freehand. It contains all of the useful information about the shape of that function. All you need to know about it. These are the salient features. The flat gain, and in this case, single corner frequency. Those equations below are a listing of the definitions of these parameters in terms of the original circuit elements. Again, this is design-oriented because usually the design problem is you're given the gain and you're given the corner frequency. Or if it's internal to a larger design problem, these are quantities that you need to establish for some other purpose. In other words, these are the given quantities, and you have to decide what circuit elements will give those answers. That means you have to invert these two definitions and find the values of the resistors and the capacitor to give you those answers. So that's why this is a useful format in itself, even though this is still just a normal pole. Here's another example, and standard analysis this time would give you this version. And if you follow through the same steps as I did before, which is identify the salient features, then obviously the coefficient of the S in the denominator defines a corner frequency, which is a normal pole. This time the numerator has an S term, and if you define its coefficient in terms of some other normalizing frequency, omega 0, defined as this, that also is a low entropy format, but there's something missing this time. If you make a sketch of the magnitude of that function as a versus log frequency as usual, what is the physical interpretation of the omega 0? And it's not immediately obvious. So my recommendation is invert the pole. And it's easy to see algebraically how you do that. You pull out front S over omega x. That leaves behind omega x over S plus 1. And the S that comes out front cancels the 1 in the numerator. And then you get omega x over omega 0, which is a new parameter. And the reason that it's worth doing this is that when you draw the magnitude asymptotes, as I've done over on the right, these are the two parameters that are the salient features. This time, the coefficient in front is identified as the infinite frequency flat gain. Because if you let S go to infinity, the other factor goes to 1, so whatever is out front must be the infinite frequency flat gain. So give it a symbol that is appropriate for that. So I put a subscript infinity on it. The opposite of the subscript 0 that we had in the previous case for 0 frequency flat gain. So there are still two parameters that describe this shape of the asymptotes. And you see, it is just a horizontal reversal of the previous sketch. But notice the equation is also symmetrical. And the only difference compared to the previous case is that the S term itself is upside down. That corresponds one-to-one to reversing the direction of the frequency axis in the sketch, or making a horizontal reversal of the complete picture. And that works because the horizontal axis is a logarithmic scale of frequency. The basic property of logarithms is log 1 over x equals minus log x. So making a horizontal reversal of the picture is equivalent to inverting the variable, in this case the frequency. So if you simply take the normal single pole function and you turn the S term upside down, the result is a horizontal reversal of the picture. So that's what I call an inverted pole. And there's the sketch that goes with it. And that's the only value of doing this, the fact that you can visualize that sketch. Because it maintains the complete symmetry now with the two directions of the frequency axis. High frequency poles come about because of shunt capacitances usually. Low frequency poles, inverted poles, come about because of coupling, bypass, and decoupling capacitances. The significant feature is the reference gain, which is the coefficient in front, is the high frequency end of it instead of the low frequency end of it. And all that inverted poles do is expose that symmetry. It's a useful technique. Well, I started this question with what's the significance of the omega 0? Because you see, I got rid of it. But going back to that question, where is omega 0? This is where it is on that picture. It's where this sloping asymptote crosses 0 dB. Because if you substitute S equals J omega 0, that cancels the omega 0 underneath and gives you a magnitude of 1, which is 0 dB. So the point about this transformation is, if you stay with the original version, which would be the common one, then you have two parameters, omega x and omega 0. And this is where they are on the picture. There's omega x and there's omega 0. The point about that is, who cares where omega 0 is? It's not the important quantity. The A infinity is the important quantity. The point is, the omega 0 is not an interesting, useful parameter upon which to put the spotlight. The important parameter, obviously, is the flat gain. That's the only value of using inverted poles. It allows you to put the important parameters up front in the equation instead of burying them in some other parameter. That's the only value of it. Now, obviously, you can extend the same sort of notation to zeros. A 0 is simply a vertical inversion of a pole, because the entire S factor is moved from the denominator, where it's a pole, to the numerator, where you call it a 0. And the same basic feature of the logarithm applies to the vertical axis this time. Inverting the function, in this case it's the left-hand side, which is the vertical axis function, inverting the function, which means moving that factor from denominator to numerator, changes the sign of the logarithmic unit, which is equivalent to a vertical inversion. So all that happens is, as normal 0 is a concave upwards corner instead of a concave downwards corner that you had for the pole. All of the detailed geometry of the 3dB smooth curve simply carries along with it. You don't have to redraw it. Now you see the symmetry between vertical inversions, which you know about already. The horizontal inversion works just the same because it's also a logarithmic scale. And so a horizontal reversal of a normal 0 gives you an inverted 0. And again, the reason that that's useful is it allows you to retain the flat gain as the leading coefficient, the reference gain, which is obviously the most important part of the characteristic. Same argument as before, just completes the entire symmetry. Well, the reason why these are useful is they are simply building blocks for more complicated systems. Here's one where there are two flat gains and several slopes. If you write the factored pole 0 form, which is simply an accumulation of products and quotients of the other factors, you can choose either the A1 or the A2 as the reference gain and put it in front. And any corner frequency which is below the reference gain you've chosen will be in an inverted form, because the flat gain is equivalent to the infinite frequency asymptote for that particular corner, just like the little building block. Corner frequencies which are above the flat gain that you've chosen will remain in normal format. So depending on which flat gain you choose, some of the corners are inverted, some of them are normal, and I put the inverted ones in red so you can see where the change occurs when you, depending on which of the A's you care to choose. And the whole point about this is you've got the choice about which format you want to use. And which one you would choose depends on the context of the problem. Which of these flat gains is the most significant one? Which is the specification? Or whatever the context of the problem is, you can make your choice of which of those gains to use. And using inverted poles and zeros simply gives you that flexibility. That's the only value. Now, you may feel some mental resistance to adopting those, which is normal, of course. And all I can say about that is, if you don't like them, you don't have to use them. You've survived this long without them, you certainly will continue to survive without them. I simply suggest that it gives you added flexibility in maintaining a closer relationship between the parameters of the equation and the salient features of the sketches. And that can be nothing but helpful in trying to keep control of the algebra, which is the overall objective. So it's simply widening your available bag of tricks, that's all. And just to hammer that home once more, here's a slightly more complicated example. The flat gain is at infinite frequency, so representation of the three corners in inverted form is what I would recommend. So there's two inverted poles and one inverted zero. So suppose I refuse to accept that notation, and I insist on writing the result in terms of normal poles and zeros. Algebraically, of course, you can easily do that. You just bring all of these S terms out front, and that uninverts the corner frequencies, and then you get a mess of stuff in front, and when you reduce it, it comes down to an S and a single parameter omega x in the denominator. And most people would consider that the conventional format. And that's fine, of course, it's correct, but then this is the question that I raise. Omega x is obviously an important parameter in the equation. Where is it on the graph? It's implicit somewhere, because obviously it's these combinations of things, but geometrically, visually, where is it? Well, it's on the zero frequency asymptote. It's where the zero frequency asymptote crosses 0 dB. Because if you let S get very small, all this other factor goes to 1, and all you're left with is S over omega x, which is this slope. So where that crosses 0 dB is where omega x is. Now again, depends on the numbers as to whether it's there or down here or up there. That depends on numbers. But it is on the zero frequency asymptote. And so my response to that format of the answer is, who cares where omega x is? It's not an important parameter in the problem. Obviously the AM is. So by refusing to use the inverted pole zero notation, you have buried the important parameter and replaced it by an unimportant parameter. One more example. Some people wouldn't even consider this to be the standard format. They would like to see it S plus omega C, S plus omega A, and so on. So here's another example with the notation that I've recommended. And if you don't like that and you want to put them in this format, then you can do that too, algebraically. And again, you get another combination out front that turns out to be an omega y. And again, I have the same question. Where is omega y on the graph? Well, now you know by symmetry from the previous problem. It's where the infinite frequency asymptote crosses 0 dB. Because if you let S go to infinity in the rest of the factor, it goes to 1 over S, and you're left with omega y over S, which is the negative infinite frequency asymptote, and where it goes through unity magnitude is where omega y is. And it's the same conclusion as before. You don't care where omega y is. It's not an interesting quantity. And again, the important one has been buried in an unimportant one. Of course, there's good reason why this is often considered the normal conventional format. That's because when you look up tables of Laplace transforms, you usually find them expressed in that way. That's a perfectly good reason to write them like that. Again, you have the flexibility. There are different low entropy formats, and your choice of which one you want to make is determined by the context of the problem. Which one is most useful, which gives you the most direct relationships with the properties of the system. The bottom line is you have the choice. So here's another manager's bottom line. Summarizing this, corner frequencies that are concave upwards are zeros, concave downwards are poles. That's familiar, but here's the symmetry. Corner frequencies lower than the reference gain are inverted. Corner frequencies above the reference gain are normal. And again, from the manager's point of view, if you see reports that contain polynomials in S with non-unity leading terms, that means that you get sums or products of elements in the other terms, send it back. If they're not in factored pole zero form, send it back. Make sure that the reference gain has some physical interpretation, some significance to do either with the properties of the system or has something to do with the specification. Okay, next thing. And this is something that I talked about at some length a year ago, so I'll shorten it this time. This is a regression now all the way back to high school. The familiar lowly quadratic equation formula. Who will ever forget that? It's the first formula we ever learn in any field, I suspect. And it's burned into our memories. And it's burned into our memories in this standard notation, which I've discovered seems to be universal all across around the world. Everyone knows this formula in terms of those ABC coefficients of the quadratic. But I suggest a heresy. It's a lousy formula. In fact, it's lousy in two different ways. And when I talk to the Caltech students or any students, I often introduce this topic by sort of throwing out a challenge and saying, you think you know all about a quadratic equation? Well, how about these questions? There are three independent parameters, A, B, C. How many of them determine the roots? How many independent parameters determine the roots? Well, think a little bit, and usually the first answer is 3, which is wrong. Correct answer is 2 parameters determine the roots. And in fact, if you just look at this second line, you can tell that. Because the A coefficient is simply a scale factor on the whole function, and the roots x1 and x2 are determined by 2 ratios. So there are really only 2 independent parameters that determine the roots. Another question. How many independent parameters determine whether the roots are real or complex? And the answer is 1. Because if you look at this expression, the only thing that determines that the answer to that question is whether the quantity under the radical is greater than 0 or less than 0. So there's only one quantity, the stuff under the radical. That's the only thing that determines whether roots are real or complex. Well, that students find that maybe a little surprising. They hadn't thought of that. Then I suggest, well, think about tuned circuits, RLC tank circuits, in terms of resonance, damping, Q factor. Think of the question in those terms, because the RLC circuit is represented by a quadratic equation. And how many parameters determine the degree of damping? 1, the Q factor. They know that. But unless you point out that context, they don't translate it into the general question, of how many independent parameters determine the roots. Even though they really knew the answer, they don't make the connection. Well, there's still one more question. Did you know that you could express the analytic roots of a quadratic without the use of a radical sign? Well, most people don't know that. And of course it isn't exactly true in general, but to some degree of approximation, it actually can happen very commonly. And that's what I can show very quickly. Anyway, back to the reason why this equation is a lousy formula in two different ways. One of them is it's high entropy, because whenever you get a quadratic, and it comes up all the time in circuit analysis, of course, the ABC simply represent more complicated combinations of the circuit elements. And so if you write the roots of the quadratic, substituting the circuit elements in place of the ABC, all you get is a messier equation. And there's nothing you can do with it except put numbers in, which means you might as well have put numbers in for the original ABC coefficients before you wrote the equation for the roots. In other words, there's absolutely zero benefit in writing the roots in terms of the circuit elements, because looking at the equation gives you no insight whatever into how those elements affect the answer. So that's one of the reasons it's a lousy formula. It's high entropy. The other reason it's lousy is a computational difficulty. When you have the opposite sign between these two terms, in many numerical cases you end up subtracting two numbers that are almost equal. When I say many cases, if you consider the spectrum of possibilities from real roots to complex roots, real roots constitutes half of that spectrum. And it's when you have real roots that you run into that computational difficulty. So this is not an unusual situation. It is in fact an extremely common situation. In fact, almost 50% of the total cases, if you look at it in that kind of dividing line, in half of the cases of the solution of a quadratic equation, you run into numerical difficulties with one of the roots. Notice only one root, not the other. In other words, you compute two real roots with different degrees of accuracy, because your calculator has round off. Even your computer does, of course. And the root that you compute as the difference of two numbers means that the round off error moves up if the two numbers get close together. And in the seminar a year ago, I showed you a numerical example where the round off error of a 10-digit HP 15C calculator moved all the way up to the second digit. And you got an answer that was wrong by 10%. You tend to think of your pocket calculators with 8, 10, 12 digits as being perfectly good for all engineering applications where you're concerned only with 10% and most 1% accuracy. You think you never have computational problems at that level. And that's an example that disproves that instantly. In fact, it's worse than that, because what I showed last year was with the same numbers in the quadratic and the same calculator, by rearranging the equation into a different format, no approximation, you get another answer from the same calculator which is different from the first one. And that's kind of disturbing, because now you have to ask which is right. And worse than that, how do you know either one of them is right? And so, since the computational algorithm obviously has something important to do with that answer, then I proceeded to make a third algorithm which involved an approximation, which is actually the method of successive approximation. And I came up with what I claimed to be the answer correct to 9 significant figures. And indeed, it was not either one of the first 2 answers. And I attempted to convince you that was indeed the correct answer to 9 significant figures. And the irony of it was the correct answer was obtained from an approximation, and the 2 answers from the exact formula were both wrong. And the purpose of that example was to destroy your faith in that equation. So then I immediately proceeded to substitute something which I claimed was better, and this is what that result was. And it's a different algorithm. Now, you're not used to hearing that word algorithm in relationship to very elementary, simple things like the quadratic. But it's perfectly applicable to that case. A different algorithm simply means a different arrangement of the terms so that the computational solution is done in a different order. That's all it means. So I proposed rearranging these 2 conventional formats into these 2. And I think you can even see pretty easily how that comes about. The first one, well, here it is. No, I better finish this first. The first one obviously comes directly from the original format simply by pulling B over A out front. This is the one which is computationally okay because it has the plus sign between those 2 terms. It's the other root that has the computational problem, so I suggested this other format, and it comes out that it's the same square bracket with the plus sign, except it's in the denominator instead of the numerator. And that totally bypasses the computational accuracy problem, because in neither root do you have to compute the difference of 2 almost equal numbers. In fact, the square bracket is the same in both of the formulas, so when you get your calculator out, you compute that with whatever your last digit accuracy is, which means you compute both roots with the same last digit accuracy, and you don't lose the accuracy in one of them. Now, that solves the computational problem by that very simple rearrangement, but you notice it also solves the high entropy problem. Because whenever this square bracket is such that the 4ac over b squared is much less than 1, notice that the square bracket approaches 1. Which means that the formula reduced to simple ratios of the original quadratic coefficients. No radical sign. That's the elegant, alias low entropy, result of this format. The limiting case, whenever the quantity under that radical is close to 1, the entire square bracket approaches 1 as a limit, and the radical disappears. And you get simple ratios of the original quadratic coefficients, and that's a huge advantage when you substitute for the ABC in terms of the circuit elements. Here's the same thing derived from a slightly different original format, one that is more directly related to the frequency response that we've been talking about. So the x becomes the s, and I've already made the quadratic have a leading term of 1, which I'm recommending for low entropy reasons anyway. We see from the quadratic point of view that that's also an advantage because it removes the third parameter, which is actually irrelevant. And I've replaced the 2 remaining parameters that determine the roots with A1 and A2. When you factor it, that means you write the factors directly in terms of these corner frequencies, omega 1 and omega 2. And here's the new format in terms of the A1 and A2. Here's the omega 1 and here's the omega 2. there's that same square bracket again. Both of them having the plus sign, one in the numerator, one in the denominator. So all I've done is change the notation to condense it a little bit. The entire square bracket I just defined as some function f of q, and q is defined in terms of the a1 and a2. The q is the single parameter that determines whether the roots are real or complex, and I chose the symbol q because it is identical to the q of an RLC tank circuit. That's how it shows up. And here's the function f. Now, I mentioned the low entropy benefit of this is if the q is small enough, that means if you have a sufficiently heavily damped RLC tank, you get two real roots, and the f function simply approaches 1. And the most interesting thing of all about that is the little graph of that function, f versus q. Q of 0.5 is the dividing line between real and complex roots. You get two equal real roots when q is 0.5. And if q is small enough, f approaches 1, and the additional useful piece of information from looking at this picture is, look how rapidly f approaches 1 as q drops below 0.5. Very rapidly. And here's a particular interesting point. If q is even 0.3, f is already 0.9, it's already within 10% of its final asymptotic value of 1. What that allows you to say in words is the important part. Whenever your quadratic has real roots, it's a good approximation to assume that f is 1, which allows you to get rid of the radical sign, express the two roots as simple ratios of the original coefficients. And this is the handle you have on the degree of approximation. Whenever you have real roots, whenever q is 0.5 or less, notice the worst case is if q is 0.5, f is 0.5, that's only a 2 to 1 range anyway. And very rapidly below that, f approaches its asymptotic limit. So it's a good approximation to take f equals to 1 in almost every case where your quadratic has real roots. And you get those huge benefits of getting rid of the radical in the analytic formats. So here's the summary. If you write your quadratic in this normalized form, this identifies two corner frequencies, and the Q factor is evaluated directly from the original coefficients. And then you can find whether f is close to 1 or not, and you don't have to compute it. You just remember that little graph, and you can tell right away whether it's a good approximation or not. And if it is a good approximation, then you can factor the quadratic into these two real factors. Notice how simple that is. It's even easy to remember, because the first factor is simply the first two terms of the original quadratic. And the coefficient of the other factor is the ratio of the third to the second coefficient. So the way you implement this is, general procedure, whenever a quadratic shows up, it should trigger a Pavlovian reaction, which is, what is its Q factor? And all you have to do is take those two coefficients and find the Q factor. That is, you substitute numbers, which may be given or may be assumed or tentative, whatever, and you see whether the Q is bigger than 0.5 or less than 0.5. If it's less than 0.5, make the real root approximation, factor it into these two approximate real roots, no radical sign. If it's bigger than 0.5, leave it in quadratic form, because you know what the magnitude and phase shape of a quadratic is. Leave it in terms of the Q and the corner frequency. And as I said, this applies directly to the RLC circuit. Here it is in the form of a low-pass filter. Here's the quadratic you get in the denominator. The Pavlovian response is instantly define the corner frequency and the Q factor, and then see whether the Q is large or small. If it's large, you're going to get a peaked response, and this is standard second order response you find in all the handbooks. On the other hand, if Q is less than 0.5, the complex pair splits into two real roots, and here's the bottom line payoff of the approximation. Look how simple those two real roots are. Q omega 0 over Q, which are symmetric on the log scale below and above the corner frequency of the filter. Dynamically, if you consider Q as a variable, the computer animations you see are just going to be great to show all this. As the Q comes down, the peak comes down, and as you go through the transition, it separates into the two real roots, and this single slope section moves to the bottom left, and those two corners move out symmetrically. Very simple low entropy expressions. And that part of it, the handbooks don't bother to show you. But that's very useful. So again, the manager's bottom line. You see any of your people writing reports or submitting things for publication that has this horrible mess in it, send it back. You can do much better. And most of the times, the designer who came up with that result didn't even know whether the roots are real or complex. So that's why I left it in that form. But that's the first thing to find out. And if they're real, use that approximation and you strip down that mess into those two simple ratios right away. Now, there's just one further point about that. You might say, well, we haven't designed it yet, so we don't know what the numbers are, so we don't know whether the roots are real or complex. But another possibility is that the design specification requires them to be real or complex, whichever it may be. Which means that even if you don't know the numbers yet, you know you have to choose them so that it comes out to have the right format of the roots, because the specification requires it. But that's still sufficient justification for making that approximation, if that's what the specification requires. Now, here's another example. A little more complicated circuit. This is the RLC low-pass filter with triple damping. That is, it's got 3 resistors in it. The normal analysis of that for the voltage transfer function would lead to this result. It's high entropy. It's a ratio of polynomials in S without a leading term of 1. And it's a ratio of sums of products of the various circuit elements. The usual high entropy format that comes out by doing the blind algebra. There's nothing you can do with that except plug in a set of numbers. So what I recommend is, instead, we know that this is going to be a quadratic format. We know it's going to be defined in terms of normalizing parameters such as the corner frequency, the Q factor, and a third one that I haven't had time to go into, which is the characteristic resistance, root L over C. It's a third normalizing parameter. We know the final result ought to be expressed in those terms. And there are the definitions of them, up at the top here. There's the definition of the corner frequency, the characteristic resistance, and 3 Q factors corresponding to the 3 resistances. And we already know from previous treatments of this sort of problem that those are the useful parameters that will define the final performance. So here's another shortcut. And again, it's very simple, very easy. The only problem is remembering to do it. And the step is, if you know at the outset which parameters you want in the answer, get them into the statement of the problem as soon as possible. And the way you do it in this case is you invert those definitions and you express the circuit element in terms of the quantities that you want to show up in the answer. And there's even one further step. You know that what you want in the answer is not L and C. You want the inductive reactance and the capacitive reactance. So you really want SL and 1 over SC. So introduce that as well. And when you invert those definitions, this is what the circuit reactances come out to be. And you see every single one of them is proportional to R0. It's a scale factor. So any transfer function, which is a ratio, will have the R0 cancel out. So the voltage transfer function does not contain R0. And in a couple of lines, you can get this result. Now, it looks sort of messy, but I claim it's low entropy, because you can immediately see what the shape of that response is. It's a quadratic denominator, but the corner frequency of the quadratic is not omega 0, it's modified by this factor in front. And the leading coefficient is not unity, it's modified by that factor. And the coefficient of the middle term, the S term, obviously defines an overall total Q factor representing the combination of the damping effects of the individual resistors. That's the full result, no approximation. But something else useful it tells you is that if there are certain inequalities such that these products of the Q factors are much bigger than 1, which means if overall it's a fairly lightly damped circuit. In the case of power electronics, for example, if this is the output filter of a switching power supply, you know all of those Q factors are bigger than 1, because if they aren't, dump the filter. It's no use. It wouldn't be efficient enough. So you know that's a case where from the specification, even though you don't know the numbers, the specification requires certain parameters to be large compared to 1. So you can use that in the analysis, even though you don't know the numbers yet. And look how much simpler that result becomes if you dump products of these Q's relative to 1. Watch what happens when I take the overlay off. That's all that's left. Now, it hits you right away what the property of that circuit is. It's a straight quadratic in the denominator, no significant change of corner frequency, no significant change of zero frequency response. There is a change of total Q factor, which is the entire middle coefficient. But look what happens. The entire coefficient defines 1 over QT, the total Q factor. Look what a simple relationship that is in terms of the contributing Q factors. It's just like the triple parallel combination of impedances. Easy to remember, very simple low entropy result. It tells you whichever is the most significant damping factor is the smallest one. And the total Q factor will be smaller than the smallest of the 3. And that's useful information for design. In terms of power supplies, for example, the load resistor is independently specified for various other reasons. It turns out that that will never be a significant contributing component of this result. And if you want the total filter to have a Q not greater than, say, 1, then you have to rely on one of the other two damping sources to get that. The load won't give it to you. That's useful design information. In other words, there's a whole lot of useful stuff that you can derive from this expression, which is made possible by that very simple step of inverting those definitions and getting those parameters into the result right away. Okay, what I want to go through now is I've talked about all these four things which are in the first box to do with the analysis. Now I'm still in the analysis box, and I want to talk about a handful of theorems. I hate to use that word theorem in this context because that's off-putting immediately. Immediately that has the connotation of all those academic things which were worthless. And so these other names, you see, were not called theorems, and of course they aren't. They're just tricks and shortcuts. I couldn't find any better names for some of these other things, so I just had to call them theorems. Anyway, the important thing is the motivation. Why are these useful? So the thing I'd called input and output impedance theorem is useful in this way. Here's a block diagram representation of some system in which you actually have a more detailed model. And your analysis process at some stage of the iteration consists of solving your model for the voltage gain Vs to VL. That's where most of the analytic effort resides, even when you use all these other shortcuts, which I hope you would. But still, that's where the bulk of the work is. And preferentially, the answer would be expressed in factored pole zero form. Okay, well and good. That's one of the specifications. But typically, there would also be specifications on the input impedance of the system. So the usual approach to the analysis is you go back to your model and you solve for the input impedance, which is a different transfer function of the same system. Because the input impedance is VI over IS. Now remember, this is a block diagram representation. You don't know what these elements are. You have a detailed model with all the R's, L's, and C's and transistors in it. But the objective is to find ZI. That may not be obvious from your model, especially if there is feedback in the system. Because, you know, feedback modifies input and output impedances, and they are not the values that relate directly to circuit elements. So the ZI is the thing that you're trying to find by analysis, and you have to solve a transfer function to do it. And it's a different transfer function than the first one, because both its drive signal in the denominator and its dependent signal in the numerator are both different from the Vs and the VL of the first transfer function. So what happens typically is, when you do this analysis, you have just about as much work to do as you did the first time to find the voltage gain. You've probably done this lots of times. You may have noticed that when you go through that analysis to find the ZI, there are whole chunks of that derivation that resemble very closely corresponding chunks in the first derivation. Especially manipulation of things to arrange them in certain orders. You find that a lot of things you do the second time resemble closely the things you did the first time. And it happens all over again if you have to calculate the output impedance. That is a third transfer function of the same system. Make the input 0, apply a test signal at the output, solve for VL over IO. The usual approach is you go back to your model, you apply that signal source, and you go through that calculation. And again, it's just about as much work as each of the other two was. And again, you notice that whole chunks of the analysis resemble what they did the first time. you begin to get a little thought at the back of your mind, there ought to be a better way. There ought to be some way of not having to repeat the parts that are the same. But that's about as far as you get with that idea, isn't it? Because you don't know how to separate what's the same from what isn't. That's what this theorem does. It answers that question. And here's the theorem. And the trick is, you avoid repeating the parts of the analysis that are the same as the voltage gain by using the voltage gain answer to find the other two transfer functions. That's how you use the work that you've already done. You use it in the form of the first answer. This is what the theorem says. To find the output impedance of your model, you don't even have to go back and look at the model. You take the answer for the gain, A, that you already have, and you take these two simple limits with respect to the load impedance ZL. And you can do that because when you calculated the A, the ZL was in your model. So it's inside the A. So all you have to do is take those two simple limits. It takes one or two lines of algebra, and that's all. And there's even a free bonus on top of that. If you have the A in factored pole zero form, then when you take these limits, you can take the limit separately, factor by factor, which means that the answer automatically comes out in factored pole zero form. No further manipulation needed. Couldn't be easier than that. And exactly the same thing applies to the input impedance. Again, you use the answer for A that you have already, which contains the ZS, and you take those two simple limits with respect to ZS, and in a line or two of algebra, you have automatically in factored pole zero form the input impedance. Huge saving of work. Now, I'm not taking the time here to derive those. All I need to say about it is the derivation is extremely simple. And in the case of the output impedance, all that this rather strange-looking equation says, all it really says is output impedance is open circuit voltage divided by short circuit current, each of them divided by the fixed input voltage. That's all it says. So you might want to think about that a bit to see why that's the explanation and what the corresponding one is for the input impedance. There's one extension of this. Sometimes you might want to know two other input and output impedances, which I call the outside values, as distinct from the first pair, which I call the inside values, where outside and inside refers to whether the ZS and ZL are counted as part of the system or not. Now, if you want to know the outside values, which I put a prime on them, obviously there's a simple relationship with the first pair. Zi prime is Zs plus Zi, Zo prime is Zl parallel Zo, and it's very easy to write those down. But when you start to substitute factored pole zero forms, then you find you're in algebraic mess, because you have a summation to compute in both cases. And when you add two factored pole zero forms, you have to cross multiply poles and zeros, multiply them out in the numerator, and refactor a new polynomial. If it's a quadratic, then you're in good shape now. You can do that and keep it low entropy. If it's a cubic, not so good. If it's anything higher than a cubic, forget it. Well, there's other ways of approaching those, but I won't go into that here. The point is, to implement this very simple relationship turns out to be a lot of work. And you can bypass that also, because a modified version of the theorem allows you to arrive at the outside values directly. By working on the A, which is in fact at pole zero form, you take the limits factor by factor, you automatically get the two answers in fact at pole zero form. In fact, it's even easier than the first pair because there's only one limit to take instead of two. You couldn't want a much better payoff than those two pairs of formulas in terms of real value in saving work. Okay, another theorem. The extra element theorem, or EET. I find that a convenient algorithm, even though it's ambiguous, because it also stands for EE times. And it also stands for a new degree called electrical engineering technology. But nevertheless, I still like to use it to refer to this theorem. This is the only thing I'm going to talk to you about which you won't have had before in principle. All the other stuff is old stuff. You really know it all already. All I've done is try to give you a different perspective on it, how to implement it more usefully. But this involves something new that you won't have had before. Again, it's the motivation that's important. This is one of the techniques which are directly related to the iteration part of that design loop. That's how it arises. You've solved this for a system transfer function, perhaps the gain. Then you go to your simulation or your measurements, and some of it agrees with your model prediction and some of it doesn't. And you strip out the things that don't agree because of instrumentation problems, all the things that you typically have to sort out, and there's still a residual number of results that don't agree with the model, so you conclude your model needs to be changed. And typically, the change that you think would be needed would be to add another element. For example, the discrepancy in your measurement often turns out to be an additional pole in the frequency response, and you knew very well that your model was too simplified and you didn't put in the cause, so now you decide you better go back and put in a capacitor somewhere. For example, the collector base capacitor of a bipolar, or the drain gate capacitor of a MOSFET, or whatever. It's an extra element. How do you do it? You go back to your circuit model, you put the element in, and you do all of the analysis over again. And it's worse than before, because it's a more complicated circuit. And you've probably done this lots of times. Again, you notice whole chunks of it resemble totally what it was the first time. There ought to be a better way. There is. That's what the theorem does. And here's how you use it. I'm not going to derive it or prove it or give examples. We don't have time. Here's the circuit model you've already analyzed for the gain. That's the A. Call it the reference gain. And I put this condition z equals infinity on it, where z is the extra element, because when you do that calculation, you haven't thought of the z yet. It doesn't exist. That's the first answer that you get. So now later, as a result of the measured discrepancy or whatever, you decide you want to add a certain element z at a certain place. So you identify a node pair across which you want to add the extra element. There it is. And what the theorem says is, to find the result for the gain in the presence of the z, you don't have to go back to the model to recalculate the whole thing. And it's almost the same trick as the input and output impedance theorem. You use the answer you already got, the reference gain. And to accommodate the additional element, all you have to do is find a correction factor that multiplies the first answer. That's how you get the benefit of using all of the work you did already, which is most of it. All you have to do is find the correction factor. The correction factor contains the element z you're going to add, obviously, and two other parameters, zd and zn. And again, I'm not deriving this, I'll just tell you what they are. The zd and the zn are driving point impedances, DPIs, calculated at the place where you want to add the extra element. Here's how you calculate them. There's your original model. Here's how you calculate ZD. You make the original input 0. You apply an independent test source at the place where the extra element is to be placed. But it isn't there yet. And you calculate the impedance looking into the system at that point. That's what ZD is. You calculate it the same way you calculate any input impedance. Nothing new about that. Here's how you calculate Zn. This is the new technique. You apply your independent test signal at the same place where the Z is going to be added. But this time, the original input is restored. So this is double injection. Now, you're not used to doing calculations like that. What you are used to doing is single injection calculations. In other words, there's only one independent input signal at a time. Maybe you calculate different transfer functions with different inputs, but you only do them one at a time. This is something new. This is driving a system with two independent inputs simultaneously. Double injection. Now, at first sight, you see there's no benefit, no value in doing that, because if you have two independent signals, you can make any other signal in the system have any value you like. Doesn't seem much value in that, except that there may be one value that you would like more than any other. And if you have a choice of what value you might like, which one do you think you'll choose? 0. In the expectation that if you choose to make something 0, some calculations will suddenly get to be very easy. And that's a perfectly good reason to choose it. And that's what you do here. You adjust these two inputs mutually with respect to each other until the output nulls. What you've really done, of course, is being a linear system model, superposition applies. The contribution to the output from one source has been adjusted to be equal and opposite to the contribution from the other source. That's what null double injection means. So you set up that condition and you calculate the driving point impedance at the same place as before, and you get a different answer. Because this time there is another input contributing to the value of the voltage and or the current at that point. So you get a different answer, and that's the definition of Zn. So the bottom line is to use the theorem to add another impedance across this node pair. All you do is use the answer you got already, the reference gain. You calculate the two driving point impedances on the reference circuit. The element isn't there. All you have to know about the extra element is where it's going to go, but it isn't in there yet. And having done those three calculations, all you do is plug into the theorem, and that's the result for the modified gain after you put the element z in place. And the potential benefit of that is you've never calculated anything on the complete circuit in the presence of the z. You have instead assembled the answer from 3 separate pieces, each of which was calculated on the original circuit. That's the value of the theorem. There's a dual form. If you want to add an element z in series with a branch, here's the other form of the theorem. The reference value of the z is now 0 instead of infinite, and the only difference is that those correction ratios are upside down. Very powerful theorem. Well, as usual, I'm going to run out of time before I get to the end. So I'll skip the next little section, which is the 2 extra element theorem, which allows you to put 2 elements in simultaneously. And that's very convenient if the 2 elements are reactances and the rest of it is resistive, because you get the poles and zeros instantly. A very, very neat analytic trick. But I'll bypass that. Because I do want to talk a bit about the feedback theorem, even though I'm not going to have time to finish it. Here's the standard model for a single loop feedback system. Here's the standard analysis. A is the forward gain, K is the feedback ratio. You want to solve for the closed loop gain G. Here's the standard format. Maybe you know it in terms of different symbols, but you certainly recognize the format. Again, I'm going to suggest to you it's a lousy formula. It's lousy because the usual approach to analysis is you yank the feedback loop off and you calculate A. And you calculate K directly from the feedback path, and you plug into this equation and you calculate G. And the trouble with doing that is you get the wrong answer. Often. Because to begin doing that analysis, when you yank the feedback path, there is usually an interaction between the feedback box and the A box, such that when you take the K box away, you actually change the value of A, because you upset the loading. Now, people recognize that. So the next step is they try to fudge it. They try to simulate the loading by hanging something on the output of the forward path that's supposed to represent the impedance of the feedback path that you've taken away. And you can certainly fix it up that way, partially. It's easy to know what to hang on first. It's not so easy to know what to do with the other end of the impedance that you're hanging on there. And exactly the same thing is true at the front end. If you disconnect the feedback at the front end, you also upset the loading. The result is the A that you calculate is not the proper value of A that belongs in the formula. That's why you get the wrong answer. That's the problem with that format. That's why I call it lousy. Well, what are we going to do about it? What I suggest we do about it is a very simple transformation made possible by the fact that we don't care what A is in the answer. The customer is buying G. That's what the specifications refer to, the G. You, as a designer, have decided that you're going to achieve that specification by means of a feedback design. So you have invented the A. The customer couldn't care less what A is. So the trick to avoid the difficulty of calculating A is don't calculate it. And to implement that simple idea, this is all you do. Multiply top and bottom by K, so you get a 1 over K in front, and A times K is T, the loop gain. That's the standard definition. So now you've got an AK in the numerator, and that's T as well. Now, all of a sudden, with that very simple transformation, we have a much more meaningful result. Because the closed loop gain of the system is now identified as the product of two factors. The G infinity, which is simply defined as 1 over K, and the reason for that choice of symbol is because the other factor, T over 1 plus T, is almost 1. On the philosophy that if you've designed a feedback system, it's because feedback is a benefit, so you want the T to be as large as possible, and the best value of T to have is infinite, and that makes that factor go to 1, which means G approaches 1 over K in the ideal case of an infinite loop gain, and so let's just define 1 over K as a limiting value of G. So that's the reason for the subscript. Now, that is a benefit in itself, because that's the specification. It's the only thing you know before you start. It's the ideal value of your closed loop gain. And notice it's uniquely determined by K. So directly from the known specification, you can design the K box. What's left? T is not really going to be infinite. All you have to do is design your feedback loop so that T is large enough. Well, large enough for what? Large enough so that T over 1 plus T is close enough to 1, and since that's an important parameter, I've given it a special symbol, the discrepancy factor, for obvious reasons. And it's very easy to make T large enough, especially nowadays where you have IC chips with gain coming out your ears. Gain is cheap. 120 dB of gain costs less than the socket you plug it into. There's only one hard part. You've got to make T large enough over a wide enough frequency range so that the D stays close enough to 1 over the specified frequency range of the closed loop gain. And also, of course, the T determines the stability by independent considerations to do with Nyquist. That defines what your design process is for a feedback system. Define the K box directly from the specification, and all you have to deal with is T. T is the single central parameter that determines the actual closed loop gain. Notice that the A has vanished. You don't need it. Well, the next couple of pages are to do with how you calculate the G infinity, and I'll skip those because that's what you ordinarily do anyway. You simply assume zero error signal, which allows you to match the feedback signal directly with the input, and that's how you get the G. The only difference from what you normally do is to recognize that when you've done that, you have actually calculated G infinity, not G, because you assumed zero error signal, and assuming zero error signal is equivalent to assuming infinite T. So that's the only difference. I'm also going to skip the next few pages to do with the effect of feedback on impedances, input and output impedances. And I'll just summarize what's left. The point about the previous part is that the loop gain becomes the central and almost only important parameter of a feedback system. So it's very desirable to be able to measure it directly in the lab. T is a closed loop property. And those of you who measure loop gains by breaking the loop and applying a test signal have no doubt found all sorts of experimental difficulties, because as soon as you break your loop, the first thing you have to do is reestablish the DC operating points. So you have to apply a bias. And if your system has a high DC gain, switching power supplies in particular, of course, are like that, then you have a lot of trouble reestablishing the operating point before you even think of injecting the AC test signal. Well, the neat trick about that is you can completely bypass that problem also. To measure the loop gain physically in the lab, you don't have to break the loop. Instead, you can inject a test signal into the loop that remains closed, and you can still measure the loop gain directly, and the operating points remain automatically self-adjusted because the loop remains closed. Okay, we better quit there. Thank you for your attention.